The gear mechanism in an automobile is a complex electromechanical marvel, a critical juncture where the raw rotational energy of the engine is precisely modulated into usable kinetic energy for vehicle propulsion. This process is fundamentally necessary because an internal combustion engine, ICE, is a high-speed, low-torque device. Its power band, the small window of RPM where it operates most efficiently, typically spans a few thousand revolutions per minute. The wheels, however, require a vast spectrum of speeds and forces, from the slow, high-torque demand of accelerating from stop to the high-speed, low-torque demand of highway cruising. The transmission bridges this monumental gap, serving as an impulse and velocity amplifier based on the venerable mechanical principle of the lever. At its core, the gearbox operates on the concept of the gear ratio. A gear, a toothed wheel, functions as a rotating lever. When a small gear drives a large gear, the rotational speed is dramatically reduced, but the torque or rotational force is amplified proportionally. This is a crucial concept known as torque multiplication. Think of your lowest gear or first gear. It engages the smallest driving gear with the largest driven gear. The engine may be spinning at 3,000 RPM, but the output shaft is spinning perhaps only 800 RPM. This substantial speed reduction delivers the massive torque required to overcome the vehicle's static inertia, that initial resistance to movement. This force-centric state is indispensable for low-speed maneuvering or steep inclines. Conversely, as the vehicle gains speed, the driver needs to shift to progressively higher gears. These gears reverse the ratio, moving toward a larger driving gear meshing with a smaller driven gear. The effect is a rapid increase in output shaft speed, bringing it closer to the engine's RPM, but a reduction in torque. This speed-centric state, such as in fifth or sixth gear, is engineered for efficiency. The engine can now maintain a high road speed at a lower, more fuel-efficient RPM, as less brute force is needed to maintain momentum. Every gear change is a precisely calculated trade-off between speed and torque. In a manual transmission, this ratio selection is physically managed by the driver. The operation hinges on synchronization. When the driver depresses the clutch pedal, they temporarily decouple the engine from the transmission. This is the moment when the synchromesh mechanism comes into play. Synchros are small, friction-line cones that rapidly force the gear that the driver wants to select and the spline shaft to which it will lock to reach the exact same rotational velocity. Once synchronized, a sliding sleeve is mechanically engaged, locking the gear onto the shaft, completing the power transfer path for the new ratio. Releasing the clutch then reconnects the engine, and the vehicle proceeds under the new gear's parameters. This constant mesh design, utilizing helical gears with their angled teeth for quiet, gradual engagement, is the standard for modern manual gearboxes. Automatic transmissions achieve the same result through fundamentally different mechanisms. The traditional automatic uses a torque converter instead of clutch. This fluid coupling device transmits and multiplies torque hydrodynamically, allowing the engine to idle while in gear. The actual gear ratio changes are handled by an epicyclic or planetary gear set. This compact mechanism consists of a central sun gear, orbiting planet gears held in a carrier, and an outer ring gear. By selectively locking and unlocking one of these three elements using hydraulic pressure-actuated clutches and bands, the transmission can achieve multiple forward and reverse ratios from a single gear cluster. Modern automatics may use multiple planetary sets and complex electronic control units, or ECUs, to manage shifts instantaneously based on throttle position, engine load, and vehicle speed. The evolution of the gear mechanism also includes specialized transmissions like the dual-clutch transmission, DCT, and the continuously variable transmission, CVT. The DCT is essentially two separate manual transmissions operating in parallel within one housing, each with its own clutch. One side manages the odd-numbered gears, and the other manages the even. This allows the car's computer to pre-select the next gear while the current one is still engaged, resulting in shifts that are milliseconds fast and nearly seamless, and ideal for performance vehicles. The CVT, On the other hand, eschews fixed gears entirely. It uses two variable diameter pulleys connected by a belt or chain. By constantly changing the effective diameter of the pulleys, the CVT provides an infinite range of gear ratios, theoretically keeping the engine at its most optimal RPM for maximum efficiency or power at all times, a notable benefit for fuel economy. Beyond the main transmission, the power is routed to the wheels via the drive shaft and finally through the differential. Located on the driven axle, either front or rear, the differential's function is twofold. It provides a final gear reduction ratio, and more importantly, it permits the wheels to rotate at different speeds when a vehicle is cornering. In a turn, the outside wheel travels a greater distance than the inside wheel. The differential's unique gear arrangement, utilizing bevel gears, is engineered to distribute torque unevenly during cornering, allowing the outer wheel to spin faster, preventing tire scrub, strain on the axles, and maintaining vehicle stability. Without this crucial mechanism, any turning maneuver would be a violent struggle against physics. The gear mechanism, therefore, is not merely a component, but the comprehensive, calculating bridge between the engine's explosive power and the precisely managed motion of the automobile.